2.6 examples. 2.6.1 Calculating the surface temperature of the Sun. Let U of lambda T be the energy density as a function of wavelength and temperature, and denote emissive power by E of lambda T, then we know that, see the next equation, and that total radiation energy per unit volume is, see the equation. So we have, see the next equation, for the total rate of radiation per unit area of a BB. If the Sun is overhead at Earth, we have radiation emission from Sun as BB at temp T, where the emission energy is related to T by above to give E sub Sun of open brace pi r sub Sun squared close brace times unit times area over 4 pi d sub Sun minus E of A r th squared equals E sub Earth goes to E sub Sun equals r sub Sun squared over 4 d sub Sun minus E of A r th squared E sub Earth.
Thus, an observation at Earth of energy falling per unit area of, see the equation, indicates an emission rate at the Sun's surface, per unit r of, see the next equation. If we now use the relation E of lambda T equals C over 4 times AT to the 4th power, we obtain for temperature at the surface of the Sun. See the equation. 2.6.2 Wavelength of maximum energy density and relation to BB temperature. Recall the relation. See the next equation.
Alternatively, see the equation. Taking the derivative, see the next equation, which reduces to solving for, see the equation. Solving, we get, see the next equation.
From this we get the convenient relation for determining BB temperature once the wavelength of maximum energy density is determined. See the equation. For the Sun, we just computed the effective BB temperature at the surface to be T equals 8,200 to the OK, thus the wavelength with the maximal energy density is. See the next equation, which is in the UV. 2.6.3 Electron beam diffraction off of crystal. Consider a beam of electrons of uniform energy 100 eV falls in the z direction on a crystal with a cubic lattice of lattice spacing 5a times 5 times 10 to the minus 10 power times meter, aligned with the xyz axis. Write a wave function in the form of a plane wave that can be used to represent the beam of electrons. Ignore normalization. Assuming that most of the beam reflected from the crystal is reflected by the plane of atoms on the surface, what will be the angle from the to the first maximum of the diffraction pattern of the reflected electrons?
Answer. A psi sub k of r t equals ae raised to the I times wt minus k r power equals ae raised to the I times wt minus kz power. The de Broglie wavelength of an electron of electric energy E of eV is given by, see the equation, with E equals 100 in units of eV. Thus k equals 2 pi over lambda equals 5.11 times 10 to the 8th power times cm to the minus 1 power with W equals E over h over 2 pi. B. Phase difference delta equals 5 a sine theta equals n lambda. So for n equals 1 at the first maximum, theta equals the inverse sine of lambda over 5a. Thus, see the next equation. And theta equals 14.2 degrees.
2.6.4 Electron beam incident on a narrow slit. Consider a uniform beam of electrons of momentum p falls at incidence on a screen with a narrow slit of which d. The electrons passing through the slit form a spot on a second screen a distance L from the first screen. Assume L is much greater than d. What is the quantum mechanical wavelength lambda associated with the electrons? If d is much greater than lambda, what is the approximately diameter s sub 1 of the spot formed on the second screen? If lambda is much greater than d, what is the approximately diameter s sub 2 of the spot formed on the second screen? What width d sub m will give approximately the minimum diameter s sub min of the spot on the second screen?
Answer. P equals h over 2 pi k equals h over 2 pi over lambda equals h over lambda. Thus, lambda equals h over p times d times b are og of lie. D is much greater than lambda goes to have geometric optics goes to diameter image asymptotically equals diameter hole. S sub 1 almost equals d lambda is much greater than d goes to diffraction important, as lambda over d goes to infinity goes to s sub d goes to infinity. D sub 0 equals the square root of 2L lambda.
2.6.5 Electron beam incident on a diatomic molecule. A uniform beam of electrons of momentum p moves in the x direction and scatters from diatomic molecules that are aligned in the x direction. The diatomic molecules can be approximated by a model consisting of two identical scattering centers spaced a distance d equals 3 times a along the x-axis, as shown above at left. One atom, one half of the molecule, alone produces a scattering intensity, as a function of angle as shown above at center. The diatomic molecule gives a scattering intensity as shown at right. Extend the scattering diagram for the diatomic molecule over the complete range of angle to 180 degrees by an approximate, qualitative, sketch. If the energy of the electron beam is increased by a factor of 4, show qualitatively how the scattering curve will change. What is the energy in electron volts of the electrons producing the scattering curve in A?
Answer. A path length diff equals d minus x sub 1 equals d times 1 minus cosine theta. X sub 1 equals d cosine theta. Minima d times 1 minus the cosine of theta sub n equals lambda n over 2 equals n pi over k times n equals 1, 3, 5, ... Maxima d times 1 minus the cosine of theta sub m equals lambda m equals 2 pi m over k times m equals 1, 2, 3, ... n equals 1 gives theta sub n equals 41.4 to the 0 power gives the cosine of theta sub 1 equals 3/4 times enclosed with box kd equals 4 pi maxima theta sub m equals the inverse cosine of 1 minus m over 2. Theta sub 1 equals 60 raised to the exponent degrees end exponent times theta sub 2 equals 90 raised to the exponent degrees end exponent times theta sub 3 equals 120 raised to the exponent degrees end exponent theta sub 4 equals 180 raised to the exponent degrees end exponent.
B if E equals 4 E sub 0 the P equals TK equals 2 P sub 0 times K equals 2 K sub 0 times enclosed with box DK equals 2D. The new condition for maxima is theta sub m equals the inverse cosine of 1 minus m over 4 over bar so there are approximately twice as many maxima.
C. See the equations. 2.7 questions. 1. What percentage of sun's energy is radiated in the visible 4000 A minus 7000 A at Earth? 2. What is the BB radiation when T equals 2.73 K? 3. A3. 500 A wavelength light source falls on potassium producing a maximum energy photoelectron excitation of 1.6 electron volts. What is the work function for potassium? Assume Planck's constant is known. Reminder of photoelectric as photon HV work function for given material, and how we can vary V while keeping work function the same, and thereby derive H in a directly accessible experiment. 4. There are two measurements. 1. With a 2,000 A wavelength light source on aluminum, there is produced a maximum energy photoelectron excitation of 2.3 electron volts. 2. With a 3,130 A wavelength light source on aluminum, there is produced a maximum energy photoelectron excitation of 0.9 electron volts. What is the work function for potassium? Assume Planck's constant is not known, and solve for that as well.